So in this video, I just want to show you a couple of tips and tricks for finding symmetry elements in, let's say, wooden blocks or other kinds of objects, maybe natural crystals, for example. So in one video, we introduced this theorem from spherical geometry. So we have 1 over x plus 1 over y plus 1 over z should be between 1 and 3, where x, y, and z represent the possibilities of having a 2, 4, or a 3-fold or a 6-fold rotational axis. So for example, we cannot have the combination 6, 6, 2 because we took the sum 1 over 6 plus 1 over 6 plus 1 over 2, that would be less than 1. And so it would not satisfy this inequality here. So that comes out of Euler's theorems of spherical geometry. Well, there are a couple of other rules that we can use. But first I want to show you how this kind of theorem reduces the number of possibilities of combinations we can have. So if we have 2, 3, 4, and 6-fold rotational axes, we have 4 things. Let's say we want to take them 3 at a time. So we have 3 intersecting axes like this, an x and a y and a z like we had in our computational example in the previous slide. So let's say we could choose from any one of them. We would have 4 options for the first one, for x, 4 options for the second, 4 options for the third. And so out of combinatorics, this tells us that there are 64 possibilities. Well, it ends up that most of those possibilities are either impossible or some of them are going to be repeats of one another, and so we would not count them. We don't have 64 unique possibilities. There are actually only 6. The possible trios that satisfy Euler's theorem and are not a repeat of other things that we might write are 2, 2, 2, 3, 2, 2, 4, 2, 2, and 6, 2, 2. And then we can have 4, 3, 2, a 2, 3, 3, and that's usually just abbreviated as 2, 3. So 1, 2, 3, 4, 5, 6. Yeah, we've got them all. So these are the 6 possible compatible trios. Notice that that is a very small subset of the mathematical possibility of taking 4 things 3 at a time. So we have a greatly reduced subset in terms of what is possible. So it means that when we are looking for various kinds of symmetry, we can limit ourselves. There's not going to be an infinite number of possibilities. There are a couple of other theorems that can be of help. And so one of them is this. If we have a point that falls along a 2, 4, or 6-fold rotational axis. So a point along A. So if we have a point that is a center of symmetry, or an inversion point, which we denote as I, then a mirror plane must be perpendicular to the 2, 4, or 6-fold axis. This is a very handy theorem because if you find a 2, 4, or 6-fold rotational axis, and let's say you know that somewhere along that line there is a center of symmetry, then you know there has to be a mirror plane. So that's something you can look for. And you might remember one of the tricks about finding a center of symmetry is if you lay a wooden block or a natural crystal down onto some flat tables. Let's say there's some table out here and your block is sitting on it. If the side on top is the inverse of the side of the one that is on the bottom, then you do indeed have a center of symmetry. So if this body has a center of symmetry and you find a 2, 4, 6-fold axis, any one of those, then there must be a mirror that is going to be perpendicular to one of those axes. There is another theorem that says the same thing about the 1 or 3-fold axes. So let's put it this way. If a 1 or a 3-fold axes have a center of symmetry, or we'll just write it as I in this case, then the 1 turns into a bar 1, and the 3 turns into a bar 3. So in other words, they are roto-inversion axes. So if we have a 1 or a 3-fold axis, an odd-numbered axis, then we have the case that if there is a center of symmetry, it must be a bar 1 or a bar 3. They must have that kind of symmetry. And then these can be expanded a little bit further. So for example, let's say we add an I, or a center of symmetry, to something like a 2, 2, 2. Then we get the following. So taking our earlier theorem, if we have a 2-fold rotational axis and we add a center of symmetry, then there must be a mirror perpendicular. So we would have a 2 over m, 2 over m, 2 over m. If we take a 3, 2, and that's a shorthand of our 3, 2, 2 that we looked at earlier, then adding an I to a 3, 2, the odd fellow, 3 would become a bar 3, and then we would have a 2 over m. So this becomes that, and that would become that. If we have a 4, 2, 2, and we add a center of symmetry to this object, then they are all even numbers, so we would have a mirror perpendicular to each of those axes. And then we can do the same with a 6, 2, 2. And it would be a 6 over m, 2 over m, 2 over m. A 4, 3, 2, you might want to pause here, the video here, and then try to do this yourself. What would a 4, 3, 2 look like? So that would be a mirror perpendicular to the 4. The 3 being odd would become a bar 3, and then we would have the evenfold axis again would have a mirror perpendicular, so we'd write it as 2 over m. And then for 2, 3, we'll use our abbreviation for the 2, 3, 3. We'd have a 2 over m, and then a bar 3. So this is the way we generate some of the different kinds of point groups. We have this set of point groups over here to the left, and these can exist perfectly fine just by themselves. But if you found a 2, 2, 2, for example, but you also know that there is a center of symmetry, then there must be mirror planes perpendicular to each of those 2-fold axes. Similarly, if you found something that has a 4-fold and a 2-fold and a 2-fold axis, and you also know from the test we spoke of earlier that it has an I, or a center of symmetry, then there must be mirror planes perpendicular to all of those. If you have a 3, 2, but then that object has a center of symmetry, then that 3 should also act as a bar 3. So these are things you can look for when looking at wooden blocks or natural crystals.